hopefully at this point in the video series you're comfortable taking a filling diagram like this and adding electrons to it. And this is one way of representing how the electrons are around an atom. There is another representation we use, and that's called the electron configuration. Now, what you notice is that every single time we draw this filling diagram, we have the same progression of orbitals. So we have 1s, 2s, 2p, 3s, 3p, 4s, 3d. And if we want to go even higher, we've got the 4p and the 5s. This is a lot to draw, particularly if we have a lot of electrons. So let's say we have 25 electrons in our atom. Well, we could populate this with 25 electrons, but where are the valence electrons at? You don't know that intuitively. So what the electron configuration does is gives us a way of writing this by shorthand. And to do this, we're going to describe the number of electrons in each orbital with a superscript. So we've got 25 electrons. The 1s orbital can hold up to 2 electrons. So at this point we have 2 electrons. The 2s orbital can hold up to 2. So we have the 2 here and the 2 here, now we're up to 4 electrons. The p can hold up to 6. This will give us 10 electrons. 3s can hold up to 2. This will give us 12 electrons. 3p can hold up to 6. This will give us 18 electrons. So as we're moving along, the total electrons we have in this configuration so far is just the sum of the superscripts. So 2 plus 2 plus 6 plus 2 plus 6 gives us 18. Our 4s can hold up to 2, and this will give us 20 electrons. And our d can hold up to 10. But if we add 10 to these d orbitals, we'll have 30 electrons, which is more than we need for the atom. So we only need to add 5 electrons to this d. And since we don't have any 4p's, we can erase it. And we'll just get rid of this counting here. And what we get is that the electron configuration of the 25 electron atom is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. So our highest energy orbitals, the highest energy electrons are in the 3d orbital, and there are 5 of them. Now there are 5d orbitals, so can you intuit how many unpaired electrons you should have? Well, if you can't, you can go back and you can redraw the diagram. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So we have 5 unpaired electrons in the 3d orbitals. But we already see that from this. We see that we have 2 electrons in the 1s, 2 electrons in the 2s, 6 electrons in the 2p, and so forth. So if we want to write the electron configuration, instead of having to draw this whole energy diagram, we can just write the orbitals out in terms of increasing energy and start filling these orbitals until we have the correct number of electrons. Now there's one other thing we can do with this diagram, and this is used what's called the Nobel gas configuration. Now what the Nobel gas configuration does is it serves as a shorthand. So if we looked at helium, and we want to use this notation for helium. Helium has 2 electrons in it, so this would just be 1s2. If you want to work with neon, neon has a 1s2, 2s2, 2p6 electron configuration. Argon, 1s2, 2s2, 2p6, 3s2, 3p6. Now what you can see is that helium, neon, and argon all have 1s2 electrons, and so does this. Argon has 1s, 2s, and 2p electrons, and they're all filled up, and argon is 1, 2, 3 s and b orbitals filled up as well. Now, all these electrons, when we hit the Nobel gas configuration, effectively become unreactive. If we are at the Nobel gas configuration, typically an atom in this configuration does not want to accept electrons or lose electrons. And these are what are called core electrons. They are electrons that don't actually participate in any type of reaction. So instead of having to keep track of all of these electrons, what we can do is we can take the highest Nobel gas configuration, in this case, all the way up to 3p6, and replace it all with bracket AR. So if we have bracket AR, 4s2, 3d5, this is the same thing as what we had before with the 25 electrons with the 1s2, 2s2, 2p6, etc. Why use this notation? These electrons here are what are called the valence electrons. And so when we look at reactions with a 25 electron atom with any other atoms, these 7 electrons, the 4s2 and the 3d5, are the ones that are actually going to participate in the reactions. Everything else, everything in these argon configurations, the 1s electrons, the 2p electrons, the 3p electrons are not participating. So the noble gas configuration is a special subset of the electron configuration, and all it is a shorthand that emphasizes what the valence electrons are by replacing all those core electrons with just a noble gas. And this bracket AR just represents all these electrons here.